So I am going to talk about how we got to the SQL JSON features that we have now in Postgres 17. And this road starts with Google Summer of Code project in 2010. Some guy by the name Joseph Adams wrote the initial JSON implementation, the data type for JSON. This was very early in the time. I think no relational database had JSON support back then. I think Oracle got JSON support in 4 years later, and SQL Server, Oracle got JSON support two years later, and SQL Server 4 years later, or something like that. So we were the first. And it is quite possible that we were, as a participant in the relational database market, we were influential in getting the SQL committee to accept JSON into the standard. So this was written by Adams, committed eventually by Robert Haas in 2012. It appeared in Postgres 9.2 very, very early on. And the thing about this data type is that it had no internal structure. We were just storing the text. We were just parsing that the JSON was structurally correct and then storing exactly what it came in into the database. So it wasn't possible to do indexing either. So eventually, some people who had a structured data type called HStore wanted to write nested structure for HStore, and they proposed to write HStore with this nested internal binary structure, and then write JSON support, binary support for JSON based on HStore. This plan was doomed to fail because HStore was a contrib module, so it made no sense to have a data type in Postgres core depend on internals that were in a contrib module. So some people got involved. I think it was Robert Haas that eventually made, it was Andrew Dunstan that transformed the representation of, the code from being an HStore implementation to become the basis for a new data type in core Postgres, and then base HStore on top of this new data type. And because we needed a new name for this data type, somehow we came up with JSON-B. Some other names were proposed. The funniest one was something like obJSON, which was like JSON trying to use two letters, so trying to use one letter for two things in the same word, which apparently PostgreSQL is known for doing. So we got JSON-B in 2014, and this one allows for indexing, so you can have indexes pointing to specific fields in the JSON object, which of course is a huge improvement over standard JSON as a textual data type. And it has some binary storage, and it was almost a train wreck again, because at the last minute, when this was going to be released, there was a problem with the storage that caused access into the data type to be very slow because it interacted with Toast in a very bad way. So it had to be rewritten. There was some heroic efforts to get it to work correctly with Toast. Well, and that's the prehistory of things. So now coming to the present, year 2017, we got Oleg Bartunov, a longtime contributor to Postgres, who had also been involved in the HStore data type and other older stuff. He posted a giant patch to support the SQL standard syntax in the JSON, in our JSON implementation. So this was in a thread called SQL JSON in Postgres. And by the time this was posted, I had no idea that the SQL standard had a thing called SQL JSON. And I bet that many other PostgreSQL developers didn't know either that this was there. But apparently, the standard had just been released the year before, like December or November 2016. And the patch was posted in February 17. So it was really pretty new. And it was a gigantic patch, 400 kilobytes, about 1/3 of which were tests. And it was authored by Postgres Pro people Nikita Glukov, Theodor Sigaev, Oleg Bartunov, and Alexander Korotkov. And the way this was structured in the standard document, it had a series of 9 functions. So it said, well, we have the following SQL JSON functions. First, the retrieval functions, of which there are 5, and then the SQL JSON constructor functions, of which there are 4. So closing up, it says the retrieval functions are JSON value function, then JSON query, JSON table, JSON predicate, and JSON exists predicate. And if you look at this definition, it says it extracts, for instance, the JSON query one says extracts a JSON text from a JSON text. And this is what this is saying. It is referring to a definition made in the SQL 16 glossary or whatever. I don't remember what this section is called. But it says a JSON text is a sequence of JSON tokens. So essentially, you have a textual representation for JSON data that comes into the database, and it is transformed into something internally. The standard doesn't care how you manage the data internally, but it does care that you have a textual representation for it. Well, and the next set of functions is the SQL JSON construction functions, which are a JSON object constructor, a JSON array constructor, a JSON object aggregate constructor, and a JSON array aggregate constructor. Okay, so then something really bad happened because this somebody got involved in committing this gigantic patch into PostgreSQL, and it was the first commit occurred on March 22, 2022 at 17:32 p.m. And just 2 hours later, it had to be reverted because it had some terrible problem that I don't, not really important, but it had to be taken out. So it took 5 more days before it could be committed again. And then 9 large commits were made from March 27, 2022 until April the 7th. So if you are familiar with the commit fest schedule for Postgres, this was the absolute latest commit fest for the Postgres release at the time. And it was all done at the very last minute. And everybody wanted to have SQL JSON. But sadly, there were further problems that were discovered again much later, and it was quite a disaster. So from this initial 9 commits, we had 14 more commits to fix things up. And until eventually, a problem that was absolutely impossible to solve in the time constraints that we have, we made a decision that it had to be reverted completely. And the fundamental problem that we had was that the JSON the new JSON code was not handling in a proper way the need for catching parse errors. So the SQL JSON is a departure from the normal way that parsing types operate, in that you can tell the database, hey, if this fails to parse because the value is invalid, do not throw an error, but instead return null or something like that. And the way this was implemented in the original patches was that the code would try to establish a save point, then parse the error, which would, parse the data, which would throw an error, and then we would try to unwind the error state by rolling back to the save point that we had established at the beginning. And so at that point, we knew that the the JSON data was bogus, and we could return the null that the user wanted to return. But this was very inefficient, and it had some severe problems, such as if you try to parse the JSON and run out of memory, then you throw the error, but you catch the error with the save point and then report, hey, your JSON is invalid. But actually, the JSON is not invalid. The problem is that you run out of memory. So the implementation in this, it does not make sense to try to catch errors that way. And also, as I said, it is very slow. So this is when a completely new technology entered Postgres, which was extremely useful, not only for SQL JSON, but for other things also, which is called soft errors. So soft errors are a thing that allow you to save error state when it is going to be thrown into a special variable, so that the function that is doing the parsing can obtain the error state and process it in the way that it seems appropriate, without the system actually getting the error be thrown. And then that means that the system doesn't slow down processing the error redundantly, and it is more robust and it performs better. So this was done by using this new macro introduced in the code, where you would normally have e-report to throw an error, you now have e-return, which allows you to return the error, return from the function that is doing the parse without throwing. Sorry, are you?
I have a question, but I'll wait for you. When you say you ran out of memory parsing the JSON, do you mean applying statements to JSON data in the database, or parsing the actual statement itself?
Anything that can happen that is not actually a JSON parse error, that can happen while you're parsing error. For instance, if you're parsing JSON and the user presses Ctrl+C, you get an interrupt signal, and then you capture that, and then the save point captures the signal, and so that's nonsensical behavior. But out of memory, I mean, the system is running out of memory. You're running to the limit. And by parsing the JSON, you need to allocate the last few bytes.
JSON data, or parsing the SQL JSON path statement?
Okay. No, I mean parsing the JSON data.
Interesting. Okay.
So yeah, you can parse a statement, and the statement has to be parsed before it is to be executed. So it is not going to capture. This is not going to capture an error while you're parsing the statement. It's only going to capture the error while you're running the statement, executing it. So well, we have this new macro, which is actually just a call for another macro, which is error save. Which what this one does is store the error information into some variable that you have passed into it. And the nice thing about it is that if you as the caller of this macro function, you can set up an error context, an error save context. So in the source code, you will see that if you call this macro and your error context is null, then this will behave exactly as e-report. So the Postgres will throw the error in the normal way. But if you have set the error context correctly before calling this function, then the error state will be saved in there, and the parse will not fail. So once error capturing was in soft errors were introduced into the Postgres code base, then we could rebase the SQL JSON code on top of that soft error and get rid of the save point and the parsing stuff and all that. So on December 28, 2022, which is to say just before the previous to last commit fest, Amit Langotti posted a new version of the SQL JSON patch based on soft errors. This was very late in the cycle, so it seemed quite difficult to get it all done in that cycle, which was 16. So this consisted of 10 patches, each implementing a number of features. And the nice thing about this is that we could go over a few of these and introduce the features one at a time or few at a time. So I got involved at that moment, and I committed the first of those patches, the SQL JSON constructors patch, on March 29 of that year. So just before 1 week, 1 week before the commit fest ended. So it was quite late. So I committed Amit's patches 1 and 2, which included JSON array, JSON object, JSON array AG, and JSON object AG, which implemented part of the standard, if you recall, which is about SQL constructors. The 4 functions that were mentioned in that part of the standard are these 4 functions. So here we go. The first one is JSON array. This is the simplest one. So I am going to take that as an opportunity to explain the clauses in there also. So we have JSON array, open parents, value expression, optionally format JSON, and this could be repeated a number of times. Have the clause null on null or absent on null, and finally returning data type, close parents. So the way you call this is that you give it an expression and it returns a value in the array. So you can say 1 + 1 or current date, and it will represent the output of the function as a string. And then you can have a string that looks like a JSON object. So if you probably know very well that a JSON array can contain not only scalars, but also other JSON objects or other JSON arrays in there. So the first one there is not actually JSON. It is a string that looks like JSON, but with the quotes escaped. So it is just a string. But if I say format JSON, then the function understands that I am trying to install a JSON object as an array element, and then it interprets the value correctly, and it knows that what I have here is actually a JSON object.
Can you put a JSON array call within the JSON array call?
Sure.
I guess that would be the value expression.
Yeah.
Why does it escape the first object's quotes, but not the second object's quotes?
So because I used format JSON there, and that format JSON applies to just that value. So if I applied format JSON to the other one, then this one here is not a JSON. This one here is just a text.
Oh, because you're only applying format JSON. So if you wanted them both to be objects, you have to do format JSON after eq ugly.
Correct. Yeah. You can also say encoding UTF-8, but this doesn't do anything because, as I understand, it has to be always UTF-8. So, and the other form of this function is that you can give it a query. And this is very interesting because you can say select JSON array and give it whatever you want. And this a query that returns one column, and then it will convert the values returned by that query into array values.
And is that a JSON array, or is that like, I don't know, just an array value that you could then insert into an array column?
This is a JSON array.
Okay.
And here, you can use the returning clause to tell the system that this is, I am going to return, I want JSON array to return type JSONB instead of plain JSON. So this is the store type of data. And what this is saying is that, well, I am going to construct a JSON array and return please in JSONB format, to which I can apply an subscript. So this is why it is returning to me just the second element, the first element of the array, and not both, because JSONB can be subscripted. If I omit the returning JSONB clause, then this returns type JSON, and type JSON does not allow subscripting. So this would throw an error. Yeah.
Can we add our own data types to the returning? Like for example, can we do returning HStore?
Yes, you can do that, because you can return any type, as I understand, you can return any type that has a cast to JSON.
A cast, okay.
So you can do character types, JSON, JSONB, or any type that has a cast.
How do we do, like for example, the format JSON encoding UTF-8? Can we do encoding UTF-32?
So no. Yes, but you have to use, and I forgot this, you can use returning byte A also. Right. And if you're returning byte A, then you can use, I think, maybe I'm wrong.
But how can you specify what the, can you specify what the cast function is, or it's just the default cast?
Good question. I don't think there's a syntax for specifying which cast to use. Okay, so the other thing you can do is you can use this null or null clause to keep the nulls in the array. So here I am saying 1 null 3 and please keep the nulls. If I had said, or if I had omitted this clause, then it would just return 1 3 without the null in the middle. Okay. So JSON object. This is essentially the same thing, except that I have to specify both a key expression and the value expression. And I can separate those with the value keyword or a colon. Other than that, this is pretty much the same thing. So I can do, say, JSON object, the key, colon, the value, and it is going to give me that. Or another key, and I can concatenate that. Concatenate two strings to generate the key, and the value, current date. And notice that I had to apparence there because parsing this stuff is very difficult. And if you want to have the value, then it is not possible to use an expression, certain types of expressions. So if you use the colon, then passing the concatenated strings will work without the parents. But with the value keyword, it doesn't. Funny things from our Bison grammar. That is that. So I here show also that you can give the key colon null and it will be ignored. Because I have the absent on null.
You give a null as a key?
No, you cannot have null as a key. You can have null as values only. So you also have the clause with unique keys, which means that if you do have duplicate keys, then it will throw an error. So you can say without unique keys, and it will ignore them, and it will keep both, as I remember. But if you use without or omit things, then consistency problems can occur because, for instance, if you return JSON-B, which has the habit of ignoring instead of keeping both. So if you do returning JSON, then it will keep both because the data type JSON doesn't care if there are duplicates. But JSON-B does care. So if you do this, then the value will disappear and you will not know. JSON-B keeps the last value that is assigned. Okay, so next one, we have JSON array ag, which is rather different. In this case, you give a value expression. This function is an aggregate function. So you would use it to aggregate several rows. So you have a value expression that is going to be produced in the column, and it's going to be aggregated in the array. So I picked up the Pagila database, which is a part of the Sakila database from MySQL, and installed the tables so that I could use for test data. Here I am aggregating first names of actors based on last names. So the JSON array ag is aggregating the first names into the second column for each last name that occurs. Next one is JSON object ag, and this one is essentially the same thing again. So we have here I am aggregating the names of the staff working on. Oh, sorry, I didn't say about the Pagila database that it is emulating a video rental store. So we have movies, actors, stores, and staff in each store. So here I have staff for a store, and I join them for a specific store. And well, so here I create the JSON object by using the staff ID as key and the name as value. This may not be a particularly useful representation, or it is up to you, but this is how JSON object ACK will generate this type of data. So what this is useful for is to create a JSON representation of your tabular data, so that you can grab your relational data and use it to produce exportable JSON for sending to third parties. So in this way, we're thinking about JSON as an interchange format. And well, so that was the first patch that I committed. And then just before the Postgres 16 closed, I committed the isJSON predicate on March 31. Oh yes, that's correct. March 31, just 1 week before, exactly 1 week before the commit fest closed, and it contained the isJSON predicate. I told the people that I needed to focus on something else for the last week of the commit fest. So can you please finish the few review issues that are missing on the last patches? But it was a frantic time, and we didn't get anything else done. So anyway, we didn't get anything else done for 16, but it was very good to have this, at least this much, because it allowed us to have a lot of infrastructure for the patches that were going to come. So this is very trivial and really has it doesn't have any mysteries. You just give it a JSON value, and you can query whether this is a valid value or whether this is a value of a certain type. So is this a scalar? Is this an array? Is this an object? That's it. You can use this, for instance, if you're storing JSON in columns of your table for some reason, and then you want to check that it complies with certain rules. It doesn't do all that much. I mean, if you really wanted to verify that the schema is something that you want, then you need something more powerful that we don't yet have, which is JSON schema. But, well, that's not yet. So, I mean, you can use this in check constraints in your columns, for instance. So, well, after that, we closed for 16. And the next time we saw things was in June 2023. And Amit Langotti, which had now been made a committer, posted the remaining patches for the remaining features. So we had further SQL JSON functions, SQL JSON query functions, and a JSON table. So the first one of those surprised me very much because there were no additional JSON functions in the set of functions from the SQL 2016 standard that I had posted before. So I had to look up what had happened, and I was about to post a bug that we had committed features that wasn't actually in the standard. But then I realized that we had a new version of the standard that included more features. So this is a screenshot from SQL. Sorry?
You're welcome.
Oh, really? So this is a screenshot from SQL 2023. And the first one of those is JSON parse, which is the JSON function. Then we have JSON serialize, which takes a JSON object from the database and produces the text output. And the next ones are all already in SQL 16 until JSON value here, which we'll see it in a minute. And so with that, we have essentially a complete set of features in our implementation with two exceptions. One is the JSON table lacks one clause, JSON table plan, and the other is that here you see JSON simplified accessor, which is like subscripting in JSON, but a little bit more powerful. So I'm going to talk about that in a minute. For now, I am going to say that in July 26th, so 1 month after this, Amit Langotti committed the next set of value constructors. So the JSON function, the JSON scalar functions, and the JSON serialize function. This is all very simple. It just says if you have a JSON value, then it will output the value. So this looks like very useless, but actually in the SQL definition of the data type, it is implementation defined how is the JSON stored. So what this does is transform from the potentially binary representation of JSON into something that can be output. So well, there you have it. JSON scalar produces, this does the other thing. This constructs a JSON, the internal representation of JSON, of the JSON object based on the text that comes from the outside world. So that's the JSON function. The JSON scalar function constructs a JSON value exactly like the previous function, except that it only allows scalar values. So you can have arrays or objects. And finally, JSON serialize does the opposite. This one is the one that takes a JSON object that lives inside the database and produces the text representation of that value, so that you can export that to the outside world. So in essence, these three functions are inverse of each other. So that was it. In the Postgres world, I think this is not very interesting, but for completeness, it was good to have it, because then it is essentially compatible with other implementations of relational databases. Next up, and many months later, just before the commit fest for Postgres 17 was going to close, Amit Langotti committed SQL JSON query functions, which is the functions JSON query, JSON exists, and JSON value. I'm going to talk about JSON query quite a lot, and the other two not so much, because JSON query is the model that does essentially everything. But before I do that, I'm going to present my model. I am running out of time, I think. So yeah, I'm going to take. So this runs the SQL JSON functions, array arg, object arg, and so on, to produce a gigantic array of stores that have the employees for each store. Yes?
There's limited time. Do you have slides to talk about the future, like what's coming next and what your vision is for steps ahead? That's something we can get from documentation.
Well, I don't really know what's in the future. Okay, so because we got essentially everything, we're just missing a small feature in JSON table, and so well, I'm going to talk very quickly about JSON query. JSON query is a a function that takes a context item and a path expression and constructs and finds in the context item, which is just JSON data, some value that is resolved by the path expression. So the path expression is something like this. You have bracket, $store edx, close bracket, dot manager. And what this is saying is that please give me the manager of the store number 42. And notice that here I have the data in table all stores, column all data. So if I look at the result of this, you can see that here it is giving me an array of the names from staff of the stores 2 to 4 as a JSON array. So before I get into more details, I need to speak about JSON path. JSON path was a thing that was introduced in PostgreSQL 12, authored by Nikita Glukov and Theodor Tsigayev. As you may notice that it is the same people who wrote the initial JSON patch that Bartunov had posted. So essentially, they wanted to have a way to use the JSON path before we introduced all the SQL standard syntax for SQL JSON. So essentially, JSON path is a string that has funny accessors. So dollar says the context item, which means the whole document that you're talking about. .var is a variable in the passing clause, and .key, .star, and array accessors, and so on. So, but one interesting thing that you can do is that you have .function parents, which executes a function from in the JSON object that you are referring to. So, for instance, you can have an example here, which is $, the context item, and then you apply the colon, the question mark operator, which is like a where clause in the JSON. So this where clause says, well, look at the at, which means, in this case, at means one of the array elements that's in the context item, and walk through it, and then access the staff member from there, and then access the address of each staff, and then see the district inside that one, and see if that matches Santiago, then you find it. So here we get the result of people in Santiago. And so I said you can apply functions, and you have here the number of people who are in a store living in Santiago, and you have how many people work in that store. Okay. So I have only 2 minutes left, so I am going to skip over this. JSON value is the same thing, but it's more concise. You can only obtain scalars, I think. And then JSON exists is the same thing, except that it says whether the value exists or not, so it returns a Boolean. And finally, just before the commit phase ended for Postgres 17, we got JSON table with the nested clause. And JSON table is this. It says it's like multi-JSON query. So you can produce columns where each of the columns is the result of a JSON query evaluation of some JSON path. So you can have a column that's name for ordinality, which just counts values, or name type with a path, and the path that you see there is the JSON query JSON path that you are going to execute. So here I have a JSON table that queries the same data and extracts the value from the store number 42 in the array of stores, and brings the name of the manager and the address for that one. And finally, because I'm completely out of time, this is the last example, and it is showing that you can have nested columns, which you can query values inside the one JSON object. So this allows you to construct relational data from your JSON data that's coming from the outside world. So in this case, you can grab data from the outside world with JSON table, insert it into your database in relational mode, and once you want to grab that relational data and bring it out, you can use the other functions, JSON object, JSON array, and so on to construct the value that's going out. Okay, that's what I have.
Is JSON table in 17 and not reverted?
It is in 17 not reverted, with nested. So nested was committed as a separate feature because it was especially complicated. Yes?
We're going to learn, or who can I talk to about indexing? So we can use the GIN index now. The index gets pretty massive. I'm interested in learning more about what are some approaches coming in the future to make the index a lot better, a lot smaller than what we have today.
Yeah, I have no advice for that except for this. So essentially what this says is that if you're going to store relational data, do not use JSON to store it. So yeah.
I'm curious whether having use of JSON features is targeted more on to OLAP versus LTD workloads, whether someone should feel comfortable moving like having JSON used with all the new functions into the online and transactional workloads. Like, what are the performance things that people should be aware of?
So that's essentially the same thing here. It is normally not great to have a lot of your massive data that is going to be queried in a relational way into JSON, into JSON data type. So if you have, say, an EAV model, entity attribute value, then it is much better to use JSON for that. But for stuff that is going to be relational and you're going to query it in a relational way, then it is better to avoid that. Thank you.